So I hope you can see the PPT now. Anyway, in the last class, we have seen the basic assumptions we are making in limb state of flexure. So the assumptions were plane section orbital to the axis remain plane after bending. So we have a linear strain distribution. Then we have maximum strain, and so we just assume that the maximum strain in the outermost compression fiber is taken as 0.0035 during bending. That is another assumption that we make in limb state of flexure. Then we can adopt any sort of stress strain curves, but only thing is that it must match with the results of experimentation. Then next one is the tensile strength of concrete is ignored. We just assume that the concrete does not have any sort of tensile strength. Then regarding the steel reinforcement that we provide in RCC, that is the stresses in the reinforcement are derived from their respective stress strain curves. And again, you have the curves for both mild steel as well as HYSD was in IS 456. And in the present slide, you are provided with the curve corresponding to mild steel. And we have already seen that we will be taking a factor of safety of 1.15 for steel. That is the reason why we have a second curve. This is the curve which we take for our design purpose. Then another important point was the maximum strain and tension reinforcement in the section at failure shall not be less than this value. Why we were insisting to have a minimum of this value? It was to ensure that the steel is having or the structure is having proper ductility. So these things were already explained in the last class. So we are just moving further. Now, for designing a structure, before moving on to the actual design of the structure, we are just classifying the type structures into different classifications. Say, for example, we will take the case of a beam. In the first module, you will be dealing with the beams only. So when we take this case, we have three main subdivisions. That is, first of all, we have a section called as balance section. Then we have an under reinforced section, and finally we have over reinforced section. Okay. So these are the main three classifications for given for a section. So basically, if you are considering an RCC structure, say for example, let's consider a beam, say simply supported beam. How the failure of this structure can take place? What are the different possibilities by which this structure can fail? Can anyone tell me? There can be different possibilities, right? So basically, a RCC is made up of concrete and steel. So what are the main possibilities for this structure to fail? What is your opinion? So in simple words, we can say that either concrete can fail or either steel can fail. In both cases, we will consider the structure to be failed, right? So during the assumptions, we have seen that when the extreme compression fiber, when the strain is getting a value of 0.0035, we assume that the structure is failed. That is the failure of concrete. Similarly, steel can also fail. So these are the main two possible cases where we assume that the structure is failed. Okay, so based on this thing, we are just classifying the structure into three groups. So let's see in detail what these are. So first one is balance section. So basically during the assumptions we have told that when the strain in concrete, that is in the extreme fiber, is having a value of 0.0035, we assume that, please note, we assume that the member is failed. Okay, that is the failure of concrete. We assume that concrete is failed when we have a strain value of 0.0035 in the extreme fiber. Similarly, we can also see the failure of steel. So these are the two possibilities. In the balance section, this is a type of section in which both these failure will simultaneously occur. Okay, when we go on increasing the load, what will happen is that at the very instant of failure, the strain in concrete will reach a value of 0.0035 and the strain or yield stress of steel will reach simultaneously. Okay, so basically what you have to understand is that in a balance section, the failure of concrete and steel reach simultaneously. So if you see the definition, balance section are sections in which the tension steel also reaches yield strain, that is the failure strain, simultaneously as the concrete reaches the failure strain in bending. Okay, such a section is normally called as a balance section. And in the next sentence, it is given as the percentage of steel in this section is termed as critical or limited. So we will come back to this after defining under reinforced and over reinforced section. So You just, for the time being, you just understand that balance section is a section in which both concrete as well as steel fail simultaneously. By mentioning that it is failed, please understand practically it may not have failed. But only thing is that we are just making an assumption that if in this type of material, if we are having a strain value of so and so, we assume that the material is failed. Say for example, as we told in the case of concrete, when we have a strain value of 0.0035, we assume that that material is failed. But practically or in actual case, that material may be able to carry much more load. But for safety purpose or in the view of safety, we assume that once the material is having a strain value of such a value, we assume that the material is to be failed. So, and again, balance section is a section in which both the yield strain or the failure strain in concrete as well as steel reaches simultaneously at the same time. Okay, so that is the concept of balance section. Now coming to under reinforced section. So from the name itself, you can see that this section is under reinforced. So basically the predominance of reinforcement is less in this section. As you can understand from the name, it is under reinforced section. So obviously based on this name, which member will fail first? What do you say?
Steel.
So obviously we can understand that once the predominance or once the quantity of, not in the quantity, once the role of steel is less, it will, and if you are subjecting a heavy load, what will happen? Every time when we have a heavy load, the weaker section will fail. So as you can understand from this name itself, it is very under reinforced. That means the steel will fail first. So let's see the definition. Sections in which tension steel reaches yield strain at lower loads than the load at which concrete reaches failure strain are called as under reinforced section. So as we explained, what happens when we go on increasing our load from 0 to a higher value, what will happen? First, the steel will have its yield strain. That is, the failure of steel will take place at the first stage. Then only the yield strain of concrete will reach. Okay, so basically, as per our assumption, steel will fail first. That is, the yield strain in steel will be reaching at a lower level than the level in which the concrete will have its yield strain. I hope you are clear about this concept. Right. Do you need further explanation on this? So in very simple words, it is like this. The yield strain in concrete will occur only at a later stage after steel having the yield strain. Once steel is having the yield strain, then if you are further increasing the load, in a later stage, the yield strain in concrete will also occur. So that is regarding the under reinforced section. So then what can be over reinforced section? So I know there are some more sentences, some more things written there. We will come back to that later. Okay, now move on to the third thing, that is over reinforced section. What can be that? It is just the opposite of under reinforced section. Here we have over reinforced. The effect of reinforcement is very high. So what will happen? Obviously, when we have a load, concrete will fail first. Or in other words, if you are speaking, the yield strain of concrete will reach first. Okay. ഈ ഒരു കേസിൽ നിങ്ങൾ ഫെയിലിയർ എന്നുള്ള കൺസെപ്റ്റിൽ പഠിക്കാതിരിക്കുന്നതാണ് ബെറ്റർ. കാരണം ഞാൻ അതാണ് ഒരു കൺഫ്യൂഷൻ വരുന്നത് നമ്മളെപ്പോഴും. Actually, മെറ്റീരിയലിന്റെ ഫെയിലിയർ അല്ല. മെറ്റീരിയൽ is not failing here actually. The only thing is that we assume that the material to be failed once it reaches its yield strain. That is an assumed value. For example, in the case of concrete, we are assuming a yield strain of 0.0035. So as we go on increasing the load, the strain also will increase, and we will reach a stage where the yield strain of material, that is the assumed value of yield strain, reaches. So for example, in the case of concrete, we are assuming that once we have a strain value of 0.0035, the material is failed. But actually that material may not have failed. Please understand that concept. That is the reason why I am again and again stressing this point. The material may not have actually failed, but as per our assumption, once this strain value, that is the yield strain value, is reached, we assume that that material is failed. That can be steel or concrete. Okay, so I hope the concept is clear to you. And in the case of steel also, if you see the stress strain curve, say for example, so we have the yield stress here, right? This is Fy by 1.15. So once we have a strain value corresponding to this peak point, say suppose I am taking, I will get the strain value here. Once steel is having a strain value of this value that is corresponding to this peak, we will assume that our steel is also failed. But these are basically just assumptions. So if you see the stress strain curve here, say once we go on increasing the load, what will happen? Say if you take this point, we have zero strain here. We are further increasing the load and reaching another point. And if you are taking the corresponding strain, we are plotting a line downwards, and we are taking the strain here. This is the strain corresponding to this load in the steel. And again, we are increasing this load. We are with that we are getting a higher value of stress, and similarly we are getting a value for strain, and finally we will reach the yield stress of this steel, and the corresponding strain is called as yield strain. Okay, and once we have this yield strain in our steel, we assume that our steel is failed. But if you see this curve, you can see that afterwards what will happen once this steel is having this particular value. Is it failing? It is not failing actually. It can take up much more strains. If you see the idealized curve itself, you can see that it is going to a higher value of strains, and at this particular point only it is actually failing. That is, a rupture point will be there. Once upon reaching that point only, the actual steel will fail. But as per our assumption, what we will see, what we will take once this strain value, that is this lower strain value is reached in our steel member, we assume that that steel member is failed. Similarly, for our concrete, what will happen? Say once we increase the load like this, it will reach up to some particular point. Say here the strain is 0.002. Then again we can increase the load, and once it reaches this point, what will happen? It will have a strain value of 0.0035. So once we have this strain value, we assume that our concrete is failed. Okay. So that is regarding that. But please understand that in actual case, the material will be able to carry much more load. But in the view of safety, we assume that once these materials have a particular value of yield strain, we assume that material to be failed. And based on that strain value only, we are classifying the section into three groups. That is balance section, under reinforced section, and over reinforced section. And again, in balance section, this yield strain value of steel and concrete will reach simultaneously. And in the case of under reinforced section, what will happen? The yield strain of steel will reach first at a lower load, then only the yield strain of concrete will come into picture. Similarly, in the case of over reinforced section, what will happen? The yield strain of concrete will reach first, then only the yield strain of steel will reach. That is the basic criteria for classifying the section into balance section, under reinforced section, and over reinforced section. Okay. So now you understood the basic concept of this classification. Now we will come back to the first paragraph, that is which describes about the balance section, and in that we have a second line mentioning that the percentage of steel in this section is termed as critical or limiting steel percentage. So what can be the reason for stressing this point? The percentage, that is the amount of steel provided in a balance section, is normally called as critical or limiting steel percentage. What is that? Why we have such a particular name provided for this? The reason is that once we are decreasing, suppose I have 5%, say for example, I have 2% of steel provided in a beam, and that section is found to be a balance section. Suppose I am a little bit decreasing the amount of percentage of steel from 2 to 1.5%. What will happen to that section? What is your opinion? I am having a balance section in which the percentage of steel is 2%. Now what I am doing is that I am just removing one bar, and I found that now the percentage of steel provided in the section is just 1.5%. What will happen?
Reinforcement will fail first, that is under reinforced section.
Exactly correct. So what will happen is that the percentage of reinforcement in a balance section, what is the actual thing? The failure of concrete or the yield strain in concrete as well as steel will reach at the same point. Okay, and in this section, what we are doing, we are just reducing the amount of steel. So what will obviously happen? The yield strain in steel will come into picture at a lower load, or the yield strain in the steel will reach first. Then that type of section is called as under reinforced section. Similarly, in the same section where we have 2% of steel in the balance section, suppose I am increasing it to 2.5%. What will happen? Now the amount of steel is increased, so that which member will fail first? The yield strain in concrete will reach first, because we have just increased the percentage of steel provided in our balance section. So that amount of steel in a balance section is very critical. So if you are changing that, the section may change to a under reinforced section or a over reinforced section. That is the reason why we also call that amount of steel or the percentage of steel in such section is termed as critical or limiting steel percentage. So basically this is critical or limiting steel percentage. Another thing is that the neutral axis depth in this section is also called as critical or limiting neutral axis. So we will see that the neutral axis depth in this section is called as critical or limiting neutral axis. So please understand that. Let me take a section. Okay. So you know that what do you mean by a neutral axis, right? Neutral axis is an axis or a fiber where you do not experience any compression or tension. Suppose I am having a section like this. I am having a rectangular section and I have 3 reinforcement provided here. And let us assume that this is a balance section. Okay. In this balance section, if I am calculating the depth of neutral axis from the top fiber, I can mark this as, normally it is marked as XU, X suffix U, and this is called as neutral axis depth. So this is the case of a balance section. Suppose we have under reinforced section. What will happen? The amount of, or the percentage of steel will be less than that of a balance section. So as a shortcut method to remember things, please note, ഇതൊരു ചെറിയൊരു കാര്യങ്ങൾ ഓർത്തിരിക്കാൻ വേണ്ടി മാത്രം പറയുവാണ്, അല്ലാതെ ഇത് ആക്ച്വൽ സംഭവമാണെന്ന് വിചാരിക്കരുത്. ഇവിടെ സംഭവിക്കുന്നത് എന്താണ്? So the amount of steel is reduced. So basically ഈ neutral axis ന് ഒരു സ്വഭാവം ഉണ്ട്. ആരാണോ പവർഫുൾ അയാളുടെ അടുത്തേക്ക് നീങ്ങി നിൽക്കും. So neutral axis will always stand with the powerful person. So when we reduce the amount of steel, what happens? The predominance or the power of concrete will increase. So what will happen to the neutral axis? The neutral axis will just shift to a upward location. Sometimes the neutral axis will be somewhere here. Basically it will move nearer to our concrete. In the other case, when we have an over reinforced section, what will happen? The amount of reinforcement is more. The reinforcement, let us assume that the reinforcement is more powerful. In this case, what will happen for the neutral axis? Neutral axis always stays with the powerful person. So once we have an over reinforced section, the neutral axis will just shift towards the steel. So ഇത് ഞാൻ പെട്ടെന്ന് ഓർത്തിരിക്കാൻ വേണ്ടി പറഞ്ഞതേ ഉള്ളൂ, ഇങ്ങനെയൊന്നും അല്ല ആക്ച്വലി, ജസ്റ്റ് ഒരു കുറുക്കുവഴിയാണ്. See, neutral axis will always stay with the powerful person, and in an under reinforced section, the steel is weak. Let us assume that the steel is weak, so that the neutral axis will move towards the concrete, that is in the upward direction. And in the over reinforced section, what will happen? We have over reinforcement, that is the steel is very powerful, so that the neutral axis will have a tendency to shift like that. Let us study like that. Okay, and please understand, this is just merely for the study purpose. Okay, this is not what actually happening. So let's take the under reinforced case. So what will happen to the neutral axis in comparison to balance section? So let's just assume that in the balance section we have neutral axis here, and this is the neutral axis depth. And in the case of under reinforced section, as I told, the neutral axis will shift towards the concrete, that is in the upward direction. So what will happen to the depth of neutral axis? What will happen? So please tell me, if you have understood, please tell me what will happen to the depth of neutral axis. As I told you, the neutral axis in the under reinforced section, neutral axis have shifted towards the concrete. So what might have happened to the value of XU? The new XU will be this. That means the value of XU will decrease. Okay, this is the case of under reinforced section. So in the other case where we have an over reinforced section, what will happen? As I told, steel is powerful, over reinforced, and the neutral axis will shift towards the steel. So where will be our new neutral axis? This will be the neutral axis depth, new neutral axis depth. So in comparison to balance section, for under reinforced we have a smaller neutral axis depth, and for over reinforced section we have a higher value of neutral axis depth. So that is what is mentioned here. The neutral axis depth, say for example, if you are considering under reinforced section, please note here, the neutral axis depth in this section will be less than that of balance section. As we have seen now, in the case of under reinforced section, we have a smaller value for our XU. That is what is explained in this last sentence. Similarly, in the case of over reinforced section, what will happen? The neutral axis depth in this section will be more than that of balance section. That also we have seen now. So these are the main things that you should note when you explain about balance section, under reinforced section and over reinforced section. In balance section, again I am repeating, the yield strain, not the failure. Please note, during your examination, please don't write that the failure of steel or failure of concrete will occur first. That is actually not correct. The material is not failing. Only thing is that in the case of balance section, it is a section in which the tension steel reaches yield strain simultaneously as the concrete reaches the failure strain or the yield strain. Both are same thing. So please try to explain in this way in terms of yield strain and failure strain. Okay, don't tell that the material will fail. That is actually wrong. So in a balance section, it is a section in which the tension steel also reaches the yield strain simultaneously as the concrete reaches the failure strain in bending. Then the percentage of steel in this section is termed as critical or limiting steel percentage. Then we have the neutral axis depth in this section is also called as the critical or limiting neutral axis depth. Then coming to under reinforced section, it is a section in which steel reaches yield strain at a lower load than the load at which concrete reaches the failure strain. Okay. Then the percentage of steel in this section will be less than that of balance section. As the name suggests, the percentage of steel will be less here. Then the neutral axis depth in this section will be less than that of balance section. And finally, coming to the over reinforced section, it is a section in which the failure strain in concrete is reached earlier than the yield strain of steel. Okay, then the percentage of steel in this section will be obviously more than that of balance section, and the neutral axis depth in this section will be more than that of a balance section. So these are the main details of different types of section. If you are getting a question for your examination, and this is again please not very important, mostly this is a repeated question for your university examination. So you have to write all these points, as well as you have to draw different figures showing the neutral axis. Okay, say first of all for balance section you have to draw a neutral axis like this. Then for under reinforced section you have to draw a neutral axis like this. Then for over reinforced you have to draw separate sections of 3 rectangular sections. Then you have to show 3 separate neutral axes. And please draw all these figures in the same scale so that we can compare. So I hope you understood what I was meaning. So that is regarding this type of sections. Now we have just seen what are the different types of section, as well as we have also seen that what are the different assumptions made in limit state of collapse for flexure. Okay, now we are actually moving on to the real thing, that is how to deal with limit or how to ensure that the structure will not fail in limit state of collapse in flexure. Okay, so coming to this area, we can broadly classify the problems in this section into 2 groups. Okay, into 2 groups we will classify the problems. So in the first thing is analysis type of problem, and the second thing is design type of problem. And we have already explained what do you mean by analysis and design in perspective of DCS, right? So basically in the analysis what we do is that we will be provided with a section with known dimensions as well as known amount of steel. Okay, what we have to do in that case, we have to check the moment carrying capacity. Basically in flexure means we have to check for moment carrying capacity. So how much moment this section can take. Basically in flexure, failure in flexure means it will fail to carry up the moment that is acting on the structure, right? So in the analysis type of problem, we will actually find out the moment carrying capacity of the section. And moving on to the design type of problem, what will happen? We will have to find out we will be knowing the loads that is coming on the structure, and based on that what we have to do, we have to find out the dimension for the width and depth of the section, as well as the amount of steel that should be provided so that the section can safely take up the load that is expected to act on the structure. So these are the Broadly, we can classify our problems into two groups in this case. That is, one is analysis type of problem and second one is design type of problem. Okay, so now please see the figure which is given below. So in this figure, you have a rectangular section here. So if you see, we have a rectangular section. We have 3 reinforcements provided. And please note, this is a cross section. So this will be the width of the beam. And this total depth will be your total depth, normally marked as capital D. And this small d represents the effective depth. Do you know what you mean by effective depth? I hope that will be known to you. You have already covered MOS, right? So again, I am just repeating. It is the depth from the extreme compression fiber to the centroid of the reinforcement. Okay, to the centroid of this reinforcement, that is called as our effective depth, and normally it is marked using small letter d. And as I earlier mentioned, XU means it is the depth of neutral axis, and this NA is our neutral axis. So basically this is our cross section. And what is this? The second figure. This is the variation of strain across this section. So if you consider the top fiber, this top fiber, it will be experiencing this is actually the variation of strain at the time of failure, or in other words, we can say that epsilon Cu. Epsilon Cu means it is the ultimate strain in concrete. That is the failure value. What is the ultimate strain value that we can have in our concrete? As per our assumption, it is 0.0035. Okay, so basically this fiber, that is the extreme compression fiber, once we have a strain value of 0.0035 here, we can assume that our concrete material is failed. Then we have another epsilon U. Let's see what that is. And again here I have a linear variation of strain, and finally at the midpoint. So please note, there is a slight mistake here. This line must actually come at this location, this horizontal level. Okay, at the centroidal level. So at this particular point, what will happen? And there is no mistake in drawing this also, extending this also. So once we have a strain value like this, we can extend up to the bottom of the beam also. So basically, based on our first assumption, that is plane section normal to the axis remain plane even after bending, we have a linear strain distribution. Okay, so that is, this figure actually represents the variation of strain across our section. And here what we have, this is the variation of stress. Okay, and we know that the concrete below the neutral axis is actually assumed to be failed, or we just neglect the concrete below the neutral axis, and all the action stresses below the neutral axis, we will be experiencing only tensile stresses below the neutral axis, and we assume that this is the case of a simply supported beam, so that in top portion we have compression and in bottom portion we have tension. So the compression is entirely taken up by concrete and the tension is entirely taken up by our steel. So in top we will have compressive stresses, and in the bottom portion we will have tensile stresses, and this thing actually, this block actually is the stress strain or the variation of stress in concrete. Okay, so this is how the stress will vary in concrete. How we obtain this shape? So if you recall back, during the assumption, we have idealized the stress strain curve in concrete. So basically, if you look here, so on this axis, this vertical axis, what we have our stress value. Okay, and this axis, on this axis, we have our strain value. This thing is just rotated and kept here. So what was the maximum value of stress, or this value? What was this value of stress? We know that it is 0.45 FCK. Okay, so this maximum value of stress is 0.45 FCK. Okay, so basically this same shape is kept here. This thing shows the variation of stress in concrete, and this value will be 0.45 FCK, and on the bottom portion we assume that the entire tension is concentrated at the centroid of this steel section. Okay, that is why we are representing it by a single force, capital T. And this block actually shows the variation of stress, and based on this we can calculate the total compressive force, that is the area of this block, that can be represented by capital C. So basically we have a compressive force here and we have a tensile force. Is it clear up to this point? Please give me some response. Is it clear up to this point?
Yes, sir.
Any doubts?
Sir, can you repeat
Which part? Do you want me to repeat the entire thing, or just the stress block?
just on a briefly hour?
Yeah, sure. So basically, if you consider a section, a rectangular section like this, what we can do is that we can draw the variation of strain as well as variation of stress. And this figure, based on our first assumption, we know that the variation of strain in a section, in a RCC section, will be always linear. So that is the reason why we have a linear profile here. And based on our another assumption, what we assume is that we can assume that the concrete member is failed once we have a strain value of 0.0035 in the extreme compression fiber. And we know that suppose we are assuming that this is for a simply supported beam, we have our compressive stress here, right? So this is our extreme compression fiber, and this is the extreme or the maximum value of strain we can have in this diagram, this strain diagram. And this value can go up to a value of 0.0035 as per our assumption. Okay, then please don't consider this thing now. And similarly, at a bottom point or at the point corresponding to the centroid of the steel, we have the strain in yield strain of steel here. Okay, then so that is regarding this. This is the variation of strain. Then coming to the variation of stress, we will be having a block on top of this, because we know that as per our stress strain curve, which we have assumed for concrete, we know that initially our concrete will be, if you go back and see that figure, initially the concrete will be having a parabolic portion, then we will be having a, say for zero strain, what is the value? Here we have zero stress. As the strain increases, we have this parabolic portion going on, and up to a point of 0.002, we have this parabolic portion. After that, we have a straight line here up to a value of 0.0035. The same thing is plotted here. So let's see that one more time. So if you see this, it is just rotated. So basically here we will be having the stress value, and here we will be having the strain value. Okay, the axes are just swapped. So basically, if you look on to this variation of strain, this is the point where we have, I am taking five additional minutes. So this is the point where we have our zero strain. So corresponding that to that, we have zero stress here. Then as we increase the strain, what will happen? The stress also increases. So, and we know that up to a value of strain of 0.002, we have a parabolic variation. That is what is marked here. And after this is actually your 0.002 strain. After this, what will happen? After 0.002, we have a straight line portion for our stress up to a maximum strain value of 0.0035. It will be something like this. Up to 0.002, we will be having a parabolic portion. Then we have a straight line portion here. Similarly, that is regarding the concrete, and on bottom side we have our steel, which is only this much. Steel section. So basically we assume that the entire force is concentrated at the centroid of this section. Similarly, from this stress, we can convert this stress into a single force, total compressive force, and this total compressive force will be acting at the centroid of this section, this block. Okay, so basically what you have to understand is that in a RCC section subjected to flexure, we will be, if it is a case of simply supported beam, we will be having a compressive force on top, and we will be having a tensile force on bottom. Is it clear now up to this point?
Yes, sir.
So these things are with the very basics on which the limb state of collapse under flexure is developed. So that is the reason why I am stressing more here. Okay, so please try to understand the concept from here. Okay, so in the last class we have derived an expression. Say first of all, we have seen about the stress block parameters, that is alpha and beta, and we have found that the value of alpha was around 0.45 and the value of beta was, value of this beta was 0.42. From that is the distance from top fiber to the centroid, or the location where our total compressive force acting will be equal to 0.42. Those things we have already seen. After that, we have derived an expression for calculation of neutral axis. Then we have also discussed about moment of resistance, and we have seen that moment of resistance means it is the actual capacity of a section to resist the external moment. And now our main thing is We have seen that in limb state of collapse in Flexure, we will be having two types of problems. One is analysis type of problem where we are supposed to find out the actual capacity of a section. Okay, the dimensions will be prefixed. So what we have to do is basically we have to finalize, means we have to check whether the capacity of the section is enough to carry the external moments. That is regarding the analysis type of problem. And secondly, we will be having a design type of problem where we have to finalize the dimensions and amount of steel that should be provided in the section. So so for both these cases, we need to first of all calculate. Suppose we are say in the case of design problem, we are providing a section. We need to calculate what will be the capacity of the provided section, right? So basically, the capacity is nothing other than the moment of resistance, and we know that moment of resistance is the capacity of the section, and that is again an internal couple which is formed by the total compressive force and tensile force. These things we have seen in the last class. So today what we are trying to do is that we are just trying to find out a relation for calculation of moment of resistance. Okay. So is there any doubt up to this portion? Coming back, as we have seen, we will be having a total compressive force in the compressive zone, and we will be having a total tensile force of capital T, and we are represented by capital C and capital T. And we have seen that the internal couple, or in other words, the moment of resistance will be equal to the magnitude of this couple. And we can either take this C multiplied by the lever arm. Lever arm is the distance between these two forces, or I can take T and multiply with the lever arm. Okay, so that is what is written here. Moment of resistance mu is equal to C into D minus beta times XU. What is this? D minus beta times XU. You see this figure. D is our effective depth, which is the distance from the top fiber to the centroid of our reinforcement, and minus beta times XU. What is this beta times XU? You see the stress block, you can see that our total compressive force is assumed, compressive force is assumed to be acting at the centroid, and we have already calculated the value of beta for conventional concrete. Please note, is for conventional concrete. So, and we have seen that the value of beta was coming around 0.42. Okay, so basically this distance will be this distance, that is from the top fiber to the point of application of our compressive force, will be equal to beta times XU. XU is your neutral axis depth. That is the distance from this top fiber to your neutral axis. So if you separate this distance, that is beta times XU, from the D, what you will be getting is the lever arm. That is the distance between these two forces. Pretty simple, right? So basically, in order to calculate the magnitude of this couple, what we have to do, we have to multiply any one of the force, magnitude of any one of the force with respect to the lever arm. That is the distance between these two. That is what is written here. So basically, moment of resistance will be equal to C into lever arm, or that can be equal to T into lever arm. And please also understand that at any point of time, the value of total C must be equal to total T. Why? It is, as we have seen, to ensure equilibrium, we need to satisfy three conditions. That is, sigma h must be equal to 0, sigma v must be equal to 0, as well as sigma m must be equal to 0. So for ensuring that, what we need to do is that this C total horizontal force, that is sigma h, must be equal to 0. Therefore, the only possibility is that the magnitude of C must be equal to the magnitude of T. Okay, so please keep that in mind, and please understand these relations also. That is, moment of resistance is equal to any of these force multiplied by the lever arm, and in this case, lever arm is D minus beta times XU, as we have seen from this figure. Now let's take each case one by one. So let's start with the most acceptable type of section, that is under reinforced section. Why was this section preferred? What is the reason for that? Why we always prefer under reinforced section? I think I have already explained that in the class. Can anyone tell me why we always go for under reinforced section?
So that we prefer the failure,
So that?
We prefer the failure of steel before concrete.
Yeah, why we prefer that? That is
sufficient
correct.
warning is given.
Yeah, exactly. So we can get sufficient warning before the failure of the structure, or the section will be much more failing in a ductile manner. That is the exact term. The section will be basically failing in a ductile manner in comparison to over reinforced or balanced section. That is the reason why we always prefer to have a under reinforced section, and we know that in the case of under reinforced section, which material will be failing first? It will be steel. Steel will be not failing, steel will be reaching its yield strain first at a lower load in comparison to that of the load required to produce yield strain in concrete. We will proportion the area of concrete and steel in such a manner that the yield strain in steel will reach at a lower load in comparison to the yield means load required for producing the yield strain in concrete. So those things were already discussed. So such a section is actually we will be calling such a section as under reinforced section, and since the failure of steel will or the yield strain in steel will reach first in this section, what we will do is that when the moment of resistance will be calculated by considering the second case, that is total tensile force into D minus beta into XU. What can be the reason for that?
Steel is failing by tension.
Steel is
Steel is yielded by tension because steel is meant for
that
taking
is
tension.
okay. My question was this: we have two relations for calculation of moment of resistance. First one is E into D minus beta into XU, and second one is T into D minus XU. So in this case, for under reinforced section, I am telling that I will always go with the second case, that is T into our lever arm. What can be the reason for that? So basically, please consider this section. I will explain that. Say, let us assume that I am just increasing the load on the structure from 0 to a higher value. Okay. So basically, in the initial point, I am applying 0 load. So that what will be the value of C and T? What will be the value of compression and tension when I am not applying any load on the structure? Say, please assume that the self weight is also 0.
0.
Both the C and T will be 0. Now what I am doing is I am just slowly increasing my load from 0 to 1, 2. Likewise, I am just going on increasing. So what will happen to C and T? C and T also will start increasing with the increase in the external load. And please keep in mind that we are now dealing with the under reinforced section. So when we have a load, say the thing is, the yielding of steel will start at a lower load. Please keep that in mind. Now I am just increasing my load from 0 to a higher load. Say, let us assume that 50 kilonewton is needed to produce the yield strain in steel. And since we have a under reinforced section, we know that for making the yield strain in concrete, in comparison to steel, we will be requiring a higher value of load. So for sake of this example, what I am doing is I am just assuming that the yield strain can be produced in steel with a load of 50 kilonewton. Since I have an under reinforced section, let us assume that in order to produce the yield strain in concrete, we require say 70 kilonewton. 20 kilonewton higher load is required to produce yield strain in concrete. So basically, when I start increasing the load from 0 to maybe 70, which member will fail first? Since we have an under reinforced section and we have seen that only 50 kilonewton is needed to cause the assumed failure or to cause the yield strain in my steel. At this point, I can assume that my section is failed. So basically, due to this fact only, we are using the second relation because my steel is actually failing first. And in order to cause the yield strain in concrete, I require a higher load. So only based on the amount of load that we are externally applying. Say in this case, we were applying from 0 to a higher load, right? അപ്പോൾ ഞാൻ ഇങ്ങനെ കൂട്ടി വരുമ്പോഴേക്കും 50 എത്തുമ്പോൾ തന്നെ സ്റ്റീലിലുള്ള yield strain ഉണ്ടാവും. Okay, 50 kilonewton എത്തുമ്പോൾ തന്നെ നമ്മുടെ സെക്ഷൻ ഫെയിൽ ആയെന്ന് നമുക്ക് അസ്യൂം ചെയ്യാൻ പറ്റും because the yield strain in steel is already reached. So that is the reason why I am sticking on to the second part. That is, the moment of resistance is calculated using the second relation. Just give me a minute. Yeah, sorry for that. Anyway, coming back to our section. So let's see how to do this. So as we have seen, steel will be yielding first. So also please note, strain in steel is given by this relation as per our assumption, and stress in the steel is assumed to be, using factor of safety, we assume that the maximum stress or the yield stress in steel to be 0.87 Fi. So please note this. And now coming to our general relation, moment of resistance is equal to total tensile force into our lever arm. That is the value of the internal couple. And we know that the value of T will be, how can we calculate the force in steel? We know that the stress in steel is 0.87 Fy. Stress is always equal to force by area. So suppose I am multiplying this stress with respect to the area of steel provided. What I will be getting? I will be getting the total force acting in the steel. So that is what used here. So therefore T will be equal to my stress multiplied by the area of steel which is provided. Okay, so this is the relation for the total tensile force, and this thing we have already seen in previous slides also. So now I am just substituting this into my general expression for moment of resistance. Therefore, mu will be equal to my total force, tensile force, that is 0.87 Fy into AST into D minus 0.42 XU. This is nothing other than the lever arm. We have seen that the lever arm will be equal to D minus beta times our neutral axis depth. So substituting these things, I will get it as D minus 0.42 XU. Now, what I am doing is that, as you have seen in the case of neutral axis also, we usually express that in terms of the effective depth. We have expressed the neutral axis as XU by D, right? So similarly, in order to get such a general thing, what I am doing is that from this bracket I am just taking this D outside. Okay, from this bracket I am taking this D outside. So what will happen? I will get 0.87 Fy AST and this D multiplied by, since I have taken this D outside, I will be having a 1 here. So I have put that minus 42 XU. I have taken a D commonly from this bracket. Therefore, what I should do is I have to divide this second term with respect to D. So that is what is written here. So once I am taking this thing out, I will get a general form like this, XU by D. And this is, we have already calculated a relation for finding out the neutral axis depth like this. XU by D was equal to, what was that relation? Are you remembering that? 0.87 Fy. So we have already derived that 0.87 Fy AST by 0.36 FCK into BD. Now what I will do is that in this expression, instead of this XU by D, I will substitute that relation. So that is what is going to happen. So mu, basically we know that XU is equal to 0.87 Fy AST by 0.36 FCK into BD. And we have seen reached up to this level, that is 0.87 Fy AST into D into 1 minus 0.42 XU by D. So instead of this XU by D, now I will be substituting this value. This is nothing other than the value for XU by D. Okay. So once I substitute this, if you see here, you can see that there is a numerical thing here, that is 0.42 into 0.87 by 0.36. If you find the final value of this thing, you will obtain it as 1.005, which is approximately equal to 1 itself. So I am taking that as 1. Therefore, what will be my final expression? My final expression will be mu is equal to 0.87 Fy AST into D into 1 minus Fy into AST by FCK into BD. This thing is assumed to be equal to 1. So that is what is written here. And this is the final expression for moment of resistance, which we will be using if we are designing or analyzing a under reinforced section. Please note, this will be the final expression that we will be using for analysis or design type of problem for the calculation of moment of resistance in the case of a under reinforced section. Is it clear? Is there any doubt in this? For anyone? Any doubts at any stage of this derivation? This is important actually in point of your examination also. Sometimes they will be asking to derive these expressions. I hope it is clear to you. So, so let's proceed one more step further. Now, what I am doing is that I am tools and like here module main analysis and design tools and tools in the sense relations. Okay, so first of all, I have seen that suppose I know the value of AST which is provided in this section, how can I calculate moment of resistance? For that only I have just derived this expression. Okay, suppose second case is there where I am not interested in directly specifying the AST, that is the amount of steel that is there, but I am talking in terms of percentage of steel provided in there. What do you mean by percentage of steel in a section? What is percentage of steel? Suppose, say, let's take this figure, so it will be more clear to you. So if you see this section, you can see that we have a rectangular section like this, and this is entirely made up of concrete, and inside this we are putting our reinforcement steel. Suppose I have 3 8 mm bars inside this. Okay, These bars are having a diameter of 8 mm and I have 3 bars. So what will be the total area of steel in this? It will be 3 times 5 by 4 into 8 square, right? Since we have 3 sections, we will be having 3 times 5 by 4 into 8 square. That will give me the area of steel. This area divided by the total area of concrete, that is B into D. So our AST divided by B into D, the entire section, into 100. That is what we will be calling as our percentage of steel. With respect to the total area of concrete, how much is our steel? That is what is represented by percentage of steel, or in short, we will call it as PT. Okay, so basically PT is equal to AST divided by BD into 100. Now I am just going to convert this expression, the expression which we have derived now, in terms of PT. For that, what I will be using is, I will be using the relation connecting AST and PT. So if you see the relation which we have derived, you can see that there is a term called AST here as well as here. So from the second relation, I can represent AST as PT into BD divided by 100, right? From this relation, AST will be equal to PT into BD divided by 100. So this thing will be substituted here. Instead of this AST, I will be substituting that. So what will happen? So it will be 0.87 Fi. Instead of AST, I will be substituting PT into BD by 100. So PT by 100 into BD. D is here, and you can see here we have a D square y, because here we were already having a D here in this expression. So from this BD, again we have a D here, therefore the final thing will be BD square. So PT into BD square by 100 into 1 minus Fi by FCK. And again, if you see here we have a AST, so instead of this, what I should substitute is PT into BD into BD by 100. But you can see that here in the denominator we have a BD, so these things will cancel out, and finally I will be having PT by 100 alone. Okay, so I will get a new expression like this. So from this expression, it is a standard practice to express MU, this expression like this, that is in terms of MU by BD square. Therefore, MU by BD square will be equal to the remaining thing, that is 0.87 Fi PT by 100 into 1 minus Fi by FCK into PT by 100. Is it clear now? Any doubts in this? Direct substitution, there is nothing else. So I hope it is clear for you. Now, that was regarding our under reinforced section. Now let's see. So we have already discussed that we can go for under reinforced section or balance section. Only thing is that we don't prefer to have a over reinforced section. So basically, if we are going with the balance section also, we need to calculate the amount of this moment of resistance, capacity of our balance section also, right? So sometimes there will be a situation where you will be specifically in need of designing a section as a balance section. Sometimes you will be in need of designing the section as a under reinforced section also. So both these cases can arise. So let's see how to find out the moment of resistance. Suppose you are going to design or going with a balance section. So in the balance section, we know in comparison to under reinforced section, in the case of balance section, both the yield strain in concrete as well as steel will reach simultaneously. Okay. And again, we know that the failure of concrete is more critical, right? In comparison to steel, the failure of concrete is more critical. So when we derive the expression for moment of resistance in the case of balance section, we will stick on to the value of compressive force rather than tensile force. Anyway, both the values must be same as per our theory. But when we derive this, in this derivation, at least I am just sticking on to the value of compressive force. So again, as per our general expression, moment of resistance is equal to C or T into lever arm. In this case, both will reach at a simultaneously at the same time. That is what we call as a balance section. And again, you know that the value of C is equal to 0.36 FCK B into XU. Okay. So our general expression was total compressive force was 0.36 FCK B into XU. But if you remember back, when we defined about balance section, we have specifically told that the percentage of steel in this section is called as critical percentage of steel, and also this neutral axis is the limiting neutral axis, because if this neutral axis is reducing, say suppose the x limit is around 200 and suppose this neutral axis is going to be 180, what will happen to the section? Neutral axis for barren section is say 200 millimeters, and suppose I am reducing this, getting a value of 180 as my neutral axis, the section will change to another type of section, and again in that case what will be the type of section? Neutral axis, value of neutral axis is less in comparison to barren section.
Under reinforced.
It will be
Under
under reinforced section, right? So that is the reason why we also call the neutral axis in the case of a balanced section as limiting neutral axis represented by x limit, like this. Okay. Okay, that is so basically our expression can be written like this: 0.36 FCK b into, instead of xu I am just substituting x limit. Okay, and again please note this is again the same thing, neutral axis. Since it is the neutral axis of balanced section, we are just representing it by another variable called as x limit. That's all. Now substituting this value in our general expression for moment of resistance, mu is equal to my c into lever arm, that is 0.36 FCK b into x limit into my lever arm. Lever arm is again b minus 0.42 times. In this, instead of xu, again I am substituting x limit to represent that as the neutral axis depth of my barren section. Okay, so don't just confuse between xu and xu limit. In some text they represent it as xu limit also. That doesn't matter. Only thing is that please understand that xu limit or x limit is actually the depth of neutral axis in the case of a barren section. That's all. Now, as we have done earlier, what here I am doing is that I am just taking a d outside. Okay, so d, first of all I am just taking out my d. So what will happen? I will get a d here. Here I will have a 1 minus 0.42 x limit by d. Now what I am doing is that again I am multiplying with respect to AD. Now already I have a d, and with respect to this relation in numerator and denominator I am just multiplying another d, so that in numerator I will get it as I have a b here, so b into d square, and in the denominator also I will be having a d. So what can be the reason for this? Why I should again multiply with a d? That is because I just want to express all the x limit in terms of d, x limit as d, x limit by d or xu by d. In the previous case also we had seen that we have taken d outside only for the purpose of expressing that as x by d. Okay, so here also I am doing the same thing. First of all I have taken a d outside in order to express this x limit as x limit by d. Then when I found that I have one more x limit here, I have just multiplied a d here and divided a d here. So that is how I will arrive at this stage. So in this stage, my expression will be 0.36 FCK x limit by d into 1 minus 0.42 x limit by d into bd square. As you can see from this slide, it will be like this. So here, then I am just rearranging this. I am putting this in brackets x limit by d. That's the reason for this. I will just tell you now. So finally, I am getting the same thing. That is, as we expressed in the previous case, I am just expressing it as mu by vd square is equal to 0.36 x limit by d into 1 minus 0.42 x limit by d into fck. Okay, so this is the general expression that we use for calculation of moment of resistance in terms of, or for the case of a barren section. Okay, so you have to by heart these relations. mu by vd square is equal to 0.36 x limit by d. And again, I would like to share with you, all these relations are actually available in your code, but it is better to by heart these things. So these are frequently required, and we cannot always go and refer the codes whenever we need this type of relation. As a civil engineer, you must be able to know these relations. So that is how we will calculate the moment of resistance in the case of a barren section. Now I have told you I have put this x limit by d in brackets for a specific reason. I will just go through that now. So if you refer your IS code, have you got your IS code, IS 456?
Yes, sir. Yes, sir.
Okay, so in that, if you go to page number 70, I think it is page number 70. Let me take. I have a soft copy with me. Yes. think it is in page number 70 itself. 75. Yeah, exactly. So if you come to this page number 70 in your IS code, you have a small table here. I think you can see this PDF, right? Can you see this PDF?
Yes,
Yes,
sir.
sir.
Yeah. Okay. So if you see here, you have a small table here in which what is given here? The limiting value of depth of neutral axis for different grades of steel based on assumption 38.1 are as follows. Okay, so for different grades of steel, we have limiting neutral axis. What do you mean by limiting value of depth of neutral axis? What do you mean by that? That is nothing other than the neutral axis depth of our balance section. That is what is we called as limiting neutral axis or limiting value of neutral axis, whatever terminologies we use. The thing is, it is the neutral axis depth of a balance section. So if you see, based on the grade of steel, our standards suggest these values. Actually, these values can be easily derived based on this assumption. But anyway, I am not spending much time on that. You please understand, we have a table here and corresponding to each grade of steel, they have just given the value of XU max by D. That is the depth of neutral axis. Say, for example, if we are providing FE 250 sections, then the depth of neutral axis will be 0.53. That is the value of XU max by D or X limit by D, whatever you call. The value will be 0.53, and if you are providing HYSD bar having a strength of 415, the value of XU max by D will be 0.48, and similarly for 500 it will be 0.46. Now coming back to this slide. So the same thing is given here. So what you can do is that you can directly get, say, once you finalize what type of steel you will be providing, you can directly get the value of X limit by D from your standard specification, that is IS 456, and substitute in this relation. That is the reason why I have specifically highlighted this term, that is X limit by D. This value can be directly taken from our code with respect to or based on the type of steel which we are providing. And again, I advise you to learn these values also for each type of. Normally, we will be using FE 500 or 450. So it is better to learn these values. And for your competitive examinations and all, these things will be again asked. So what is the limiting value of neutral axis in the case of a HYSD bar? In brackets, you will be having some values, and you will have to choose from them. So it is always good to practice from now itself to learn these things. Now again, since I know the value of X limit by D for each type of steel, if you come to this, suppose I am going to use mild steel, what I can do? I can just substitute the value of 0.53 instead of X limit by D in this expression at both these locations. So once I do that and simplify, I will be getting an expression like this. For mild steel, my limiting moment of resistance or the maximum capacity of a balance section will be 0.1489 FCK into BD square. Upon simplifying this, I will get like this. For 415, if I am substituting instead of XU limit by D, I am substituting 0.48. I will get an expression like this, and for FE 500 also I can form an expression like this. If you are interested, you can learn these expressions, but I don't suggest that anyway, because we have these values, and suppose we are finalizing which type of steel, we can directly substitute in this relation and find out the value. Or if you are good in learning things, you can also by heart these relations so that you can speedily do the problems. That's all. So anyway, today it's time. So we will stop it here. In the next class, actually, what we intend is that in a similar fashion, we have gone with our under info section. We will try to express things in terms of PT limit, that is percentage of steel. After that, we will see how to do the analysis type of problem. That is how to find out the moment. What are the steps in finding out the moment of resistance or the capacity, evaluating the capacity of our sections. Then we will also see the procedure on a very brief procedure on how to do the design. And please note, in the first module, you are not actually doing the complete design. Very minimal thing we are actually doing in the first module. So once we do a few problems from these two sections, very small type of problems, this module will be completed. And after that, we will start with our second module, which deals with limit state of shear. Okay. So that's it for today. Anyway, thank you for attending this section. Hope things are clear for you. If there is any doubts, please do ask it.